every single query is shipping your users' data to data centers that you don't know where they're located and what processing they're doing. Multiply that by approximately 1,000 customers using your product every day. The cloud was making it slow, expensive, and a privacy liability. What would it take to just not use the cloud? 14 gigs on the left, 6 gigs on the right, and those 6 gigs are basically shared with your other applications. You only lose 3% accuracy and decrease the memory by more than 70%. So you can prune 50 to 90% of the layers, and the model will still function. Distillation compresses the knowledge from 14 gigabytes that couldn't leave the data center to 2 gigabytes that can run in the palm of your hands. Okay, so before I begin with the talk, I want to begin with the why. How much does it cost to inference an LLM today, approximately? It's 1 penny, right? It doesn't sound like much. But multiply that by approximately 1,000 customers. Multiply that by the customers using your product every day. And now imagine you're the CTO signing that check. And on top of that, every single query is shipping your users' data to data centers that you don't know where they're located and what processing they're doing. This is how I began my journey, not with compression theory, with frustration. When I was building my previous AI startup, the cloud was making it slow, expensive, and a privacy liability. So I asked a very simple question: what would it take to just not use the cloud? And you hit these 3 very self-evident walls. You can read the numbers over here. You can negotiate the cost, you can maybe compromise on the latency, but privacy is really a non-negotiable for many industries, including healthcare, finance, government, defense. And so the minute a hospital wants to use your product, it's basically a deal breaker. So this took me back to when operating systems were decentralized, right? Then they came onto your local computer, then they became smaller, and ultimately in the palm of your hands, in your mobile phone right here. So I said, okay, can I actually make an LLM run on my mobile phone? And that was my curiosity project at Lost Funk for 7 weeks. This is the first wall I hit over here, right? 14 gigs on the left, 6 gigs on the right. And those 6 gigs are basically shared with your other applications, operating system, notifications, all of it. So can we fit an elephant in a shoebox? And the answer is yes, but we need 3 different techniques right here. So the first one over here is quantization, right? With a show of hands, how many of you over here are familiar with it? Okay, so I think majority of you. So reduce precision, save memory, that's the story. But what's worth pausing on is why it works so well. When you're basically compressing from 65,536 possible values to 16 possible values, that should be catastrophic, right? But it's not, because you only lose 3% accuracy and decrease the memory by more than 70%. And the reason is that neural networks are noisy by design. Random initialization, dropouts, stochastic gradient descent, they're built to tolerate imprecision. Rounding is just another source of noise over here. But till when? Till when can you keep on quantizing? And as we see this, FP16 baseline has a perplexity of 5.47 on a Llama 7 billion model. 4-bit is okay, maybe increases it like by 3 to 4%. 3-bit, you're kind of in the tumultuous area. And at 2-bit, you reach the point where it could potentially start producing jargon. So there's a floor below which quantization alone can't go. And that floor sits right above where we need to be. So what do? We use our second tool over here. And that is pruning. With a show of hands, how many of you over here are familiar with it? Okay, great. So score each weight by importance and remove the lowest. You know the drill. What's striking is the scale. In most neural networks, you can prune 50 to 90% of the layers, and the model will still function. That's the crazy part. You can go from a 7 billion parameter model to actually a 1 billion parameter model, which might not be the best, but it's still going to be a functional model. So the question isn't whether to prune or not to prune, it's where to prune. And that's what you can't prune uniformly because all layers are not the same. So if you prune an MLP layer, that's going to be 63 times more catastrophic than pruning an attention layer. And Apple found a single weight, one super weight. Out of 7 billion weights, if you prune this one weight, your perplexity will go from 7 to 764. I ran a bunch of ablations and with attention removed, with MLP removed, and you can see how catastrophic it was when I removed 8 MLPs in a Llama 7B model. And what's the third tool now? So distillation. So quantization and pruning basically compress the weights, but distillation compresses the knowledge. The student doesn't just learn what the teacher model has to say, it learns the probability distributions of it. So if I give it an image of a cat, it might say 85% cat, 10% dog, 5% lynx. And that uncertainty is very, very valuable to a student model. And that's what makes it so powerful over here. But how powerful actually? This powerful that companies actually willing to distill other companies' models, risking IP infringement, legal lawsuits, reputations, everything. And honestly, this is one of the best sources of model compression. So what should I do over here? Can I combine all three techniques and produce something valuable? For the scope of this project, I basically combined quantization and pruning because distillation happens afterwards anyway. And that is when I came up with Cobra. So compression via Bayesian optimized reweighted allocation or Mahalanobis vector quantization. So it's very simple actually. You have 3 steps. Measure what matters, allocate your bits accordingly, and then verify. We saw layers differ wildly in terms of their sensitivity, and Cobra exploits exactly that. It gives every layer a custom compression recipe instead of giving the entire model a one-size-fits-all compression recipe. And over here, the first step is actually measuring what matters, right? So we perturb the layers and measure how much damage it causes. The proxy metric over here is Hessian sensitivity. So look at the pattern. The first few layers and the last few layers are practically untouchable. The middle is where the opportunity lies. The first few layers are learning basic representations, tokenization, syntax, fundamental patterns. And the last one's actually decoding back to natural language. The middle ones are potentially applying minor transformations that we could do without, or maybe compromise on the quality of those transformations. Okay, so now we know where to cut. Let's actually begin cutting. So now we actually have to allocate bits and allocate sparsity. And which algorithm do you think we should use for this? The most complex one that comes to your mind for allocation. Any ideas? I tried an RL, I tried a GNN, I tried multiple different ones. Guesses, which one worked best? A greedy knapsack algorithm from my first year of college. So we give it a fixed memory budget and run a very basic knapsack algorithm. Sensitive layers get protected at 4-bit. Vast majority of them go down to 3-bit. And the redundant ones get pruned entirely over here. And you think of it as a budget problem, right? Every layer is basically an item in a shopping cart. The cost over here is memory, and the value is quality preserved. We can't afford everything at full price, so we see where do we compromise and where do we actually spend the money. And then the interesting part, did it actually work? Seems like it did, right? So smart allocation crushes uniform compression. But is this greedy approach ideal in your opinion, with a show of hands? So correct, it is not ideal. It's far, far from ideal. What we need on top of this is an allocator that basically guides it. And that's exactly what we get. A Bayesian optimization that's driving the greedy knapsack. So we take 12 parameters, model things the greedy algorithm misses. How errors interact across layers, how breadth affects sensitivity, and how component types behave differently. And after 200 iterations and a couple of Jarvis Lab credits, same memory, better outcome. It builds a model of what works, predicts where to look next, and zones in at the optimal in a fraction of the time compared to RL. So as you can see, 3-bit over here. That's what the greedy knapsack gave us 6.40, but BO gave us 6.17. And that's because it learned the interaction between sparsity and quantization. So it realized that basically when you're applying both sparsity and quantization, it's not as detrimental as the greedy knapsack thought it to be. And hence it produced a superior result. And it generalizes well, like, sorry. Yep, and it generalizes well. I ran this on a Llama 7B and a Mistral 7B, and there was an improvement in both cases. But 2-bit is a whole different beast. So over here at 3-bit, the question is what to compress and where to compress. At 2-bit, that stops mattering because you allocate most of the bits to 2 bits itself, right? You can't go below that realistically. So what matters over here is how you handle errors. So I ran 4 different ablations over here, and error compensation single-handedly is 2x more beneficial than every other innovation combined. So as you can see, it's a cascading effect, right? I basically quantize around something in layer number 12. That has a fallover effect to layer 13, layer 14, so on and so forth. So every time we perform an action, we have to compensate for that, and that's exactly what Hessian is doing over here. Otherwise, the whole thing would simply collapse. So 4 things if you take away nothing else from this talk. First of all, if you're running AI on device and you haven't tried 4-bit quantization, please try it because LLM will get 70% smaller and your accuracy will only go down by 3%. If you're trying 3-bit quantization for any research project or such, build a map first. There's multiple techniques. You have to experiment a lot with sensitivity analysis. If you're doing 2-bit, then there's multiple vector quantization techniques out there, but don't over-index on the technique itself. Try to index on the compensation methodologies. It's not as sexy, but it's actually what's driving the real value. And if you stack all techniques, quantization, pruning, and distillation, you go from 14 gigabytes that couldn't leave the data center to 2 gigabytes that can run in the palm of your hands. And thank you. Thank you so much, everyone.